Swayam Prabha. Digital India. Educated India.
Hello everybody. Today I am starting the lecture 2 of module 8. In the first class, that is the module 8 lecture 1 of shell, I introduced what is shell, and then I defined the shell as a stress skin, and based on that I have shown a differential equation of a stressed membrane, very popular differential equation with the Laplacian form, and I discussed the solution of this membrane with a uniform air pressure. So, that analogy is useful for evaluating the membrane stresses, because shell is acting like a stressed skin, and therefore, membrane theory is mostly applicable, and still it is used in design of fish. The membrane analysis are popular and used for design of shell. Okay. So, today our discussion will be on the classification of shell structure. We have first defined the shell as a stress skin, but how shell can be grouped into different categories, mainly on the geometry. So, geometrical classification has been adopted universally, and it is also included in our Indian Standard Code of Practice for reinforced concrete shell and folded plate. So, today I will discuss how the classification is done for the shell structure. Mainly the application of shell in civil engineering construction are of RCC. The material is reinforced concrete, and in many mechanical engineering application or aerospace engineering application, shell are of metal structure. So, in that case the difference is the material, but behavior is same. Behavior that shell acts transmits the load in plane direction, that is applicable whether shell is constructed with the different materials, say RCC or this steel. Even the aluminum or composite shells are also common in various application of aerospace structure. So, before starting the classification of shell, we have to first discuss the geometry of the shell. The shell, you can see, it is actually characterized by the curved surface, and surface is the main geometrical elements, or plane. It is the important geometrical element of the shell. Now, all the stresses and that strains etc., whatever we discuss are referred to the middle plane. So, what is middle plane? Just like our plate, middle plane is the plane, or middle surface is a plane which bisects the thickness of the shell. Say this is the thickness of the shell, and middle plane is bisecting the shell. Okay. The shells are used as a roof for large area of column free space that is required for indoor stadium, assembly halls, religious places, auditorium, and in many other cases. And also the shells are applied, or shells are used, adopted in pressure vessels, pipes, liquid storage or grain storage structures, cooling tower, etc., and different geometrical forms are given to the shell structure to resist the load. So, geometry is most important thing for the shell structure, and shell is classified based on the geometry. Now, as I have told, the shell element is characterized by a surface. So, let us see what are the fundamental properties of the surface and how the surface can be represented with a parametric equations. So, here you can see a surface, and the curvature, the curved lines you are seeing in both direction, orthogonal direction, in x direction as well as in y direction. Suppose this is one direction, that is in this along the aligned along the x axis. So, in that case the y is constant, and if this line is along aligned along the Cartesian x y axis, then x is constant along this line. Okay. Now, in the parametric form, the shell is surface of the shell is represented by this function of two variables. So, x and y are the variable which governs the shell geometry. So, if the z is the coordinate which defines the elevation of the shell at any point x and y, then in the parametric form the shell surface can be represented as x is equal to x, y is equal to y, and z is a function of x and y. Now, say two points are there, say P and Q, such that this distance, the position vector of P with referred to origin O is r, and position vector of Q with reference to the origin O is r plus dr. So, these are the position vector of these 2 points P and Q, and this length P Q is the dr. Now, with reference to the origin, the position vector of point P can be represented in vectors form in 3-dimensional space, and this is given by r equal to, r is a vector here, the position vector of P. You can see it is a radial line from the origin O, and the direction is from O to P, that is the positive direction of the vector r. So, the position vector of r is nothing but, if the coordinate of P is x, y, z for example, and origin coordinate is 0, 0, 0, then position vector r will be x minus 0 into unit vector along the direction of the radial vector r, then y minus 0 into j, j is a unit vector along the Cartesian direction y. In this case, I is the unit vector along the Cartesian direction x, that is the along the x axis. So, we generally know that I, j, k are the unit vectors along the x, y and z axis. R is the vector which is directed from O to P, and magnitude of r is nothing but root over x square plus y square plus z square. So, the position vector of P can be represented by this vector r is equal to x I plus y j and z k. Now, let us see, if I can express the dr, the small distance from P to Q, with the help of the derivative of the position vector, then we will be able to find the arc length. So, we can write the vector dr equal to del r by del x into dx plus del r by del y into dy, where the vector r is differentiated, that is the partial differentiation is done here with respect to y, and here the vector r is differentiated with respect to x. Okay. Remember that r is a vector which contains 3 variables in 3-dimensional space, that variables are x, y, z. Okay. Now, let the arc length P Q is ds. Now, here P Q is shown as a straight line, it is a chord actually, but arc is ds. Now, we can represent that ds square is dr dot dr, that is the dot product of this vector P Q and P Q, that is two vector, when this is making a dot product of the two vector, then it becomes a scalar quantity. So, dr dot dr is a scalar quantity which is nothing but ds square. Okay. Now, let us substitute dr as dr by dx into dx plus del r by del y into dy. Here partial differentiation, that is with respect to r, we use the symbol del. So, del here represents the partial differential operator, and here dx is the small length along of the element along x and y along x direction, and dy is the small length of the element along the y direction. Okay. So, dot product is done here, and now if I expand this product, that means term by term multiplication if I carry out, then I will get del r by del x dot del r by del x, and dx these are scalar quantities. So, dx square plus here you will get del r by del y dot del r by del y dy square. But when you multiply or making a dot product with this and this, del r by del x into del r by del y and dx dy. Similarly, again when you make a dot product with this term del r by del y with this del r by del x, then again this term will be coming, and you know that by the property of the dot product, that is the scalar product, a dot b equal to b dot a. So, therefore, we can whatever way you multiply it, then it will be this del r by del x dot del r by del y is also equal to del r by del y dot del r by del x, but this is not true if I take the cross product of the vector. Okay. So, now since r is equal to x into I is the unit vector, y into j is also unit vector along the y axis, and z into k is unit vector along the z axis, then an x, y, z are the coordinate of p. Then if I differentiate this, because I have to use this derivative of this r in this expression, therefore, we should find out the derivative of this expression r to be and we want to substitute here to find the complete expression of ds square. Okay. Now, if you differentiate this r vector with respect to x, then it becomes, say here it I, because if you differentiate with dx by this with respect to x, this becomes 1, and therefore, this coefficient is I. I is the unit vector along the x axis. The magnitude of I is 1 and direction of I vector is along the x axis. Okay. Then if I differentiate this quantity with respect to x, then this differentiation will be 0, because y is here to be treated as a constant when it is differentiated with respect to x. Then this becomes del z by del x into k, because z is a function of x and y. So, when we differentiate, we treat this y as a constant, and therefore, we differentiate del z by del x. Okay. Similarly, when we differentiate this r vector with respect to y, we will be getting this del r by del y equal to, say here again x, if I differentiate this quantity with respect to y, then this quantity will be 0, and therefore, only this quantity will be coming, say j vector plus del z by del y, because z is a function of x and y. So, we are now getting these two vectors here, del r by del x and del r by del y. So, this can be substituted now here to again perform the dot product and then get the full expression. Okay. So, now this del r by del x, this is the expression that I have shown here, we have obtained by carrying out term by term multiplication and then substituting this derivative in this expression. So, when we substitute this, say del r by del x, that is I plus del z by del x into k dot again I plus del z by del x into k. Okay. So, we have to make the dot product of this quantity again with this quantity with again with this quantity, that is del r by del x dot del r by del x. Okay. So, here what I mean that we have to use the property of the dot product, because I dot I equal to j dot j equal to k dot k equal to 1, because by definition of dot product or scalar product, suppose two vectors are considered for dot product, say a vector and b vector lying in a plane, and the angle between the vector a and b is say theta. Then we get by definition of dot product that a dot b is equal to mod of a into mod of b into cosine of the angle between these two lines. Okay. Now, since this I vector is along the x direction or a line parallel to the x direction, similarly here also. So, when we make a dot product say with I dot I, then the angle between them will be 0. So, cos 0 is 1 and magnitude of I vector is 1. So, therefore, this quantity is 1. Similar is the j dot j and k dot k. So, when we carry out the dot product of I dot I or j dot j or k dot k, this product will be 1. Now, when we carry out the dot product of I and j vector, so I dot j. Now, what is this? I vector is along the x axis and j vector is along the y axis. So, angle between them is 90 degree. So, by definition of dot product, that vector two vectors magnitude will be there and then cosine of the angle between the two vectors. Now, cos 90 is 0. So, therefore, I dot j is 0. Similarly, j dot k and k dot I equal to 0. Now, using this property, we can now come to this expression d s square equal to 1 plus del z by del x whole square into dx square plus 2 del z by del x del z by del y into dx dy plus 1 plus del z by del y whole square into dy square. So, this is the arc length relationship ds square, and this is found from the vector relation that I have discussed in the previous slide, and this is a scalar quantity now, where del z by del x represents the slope of the curve along the x direction and del z by del y represents the slope of the curve along the y direction. So, further denoting this del z by del x by p, there is a convention that is used by one author Monks in shell structure, and this convention is followed in differential geometry to represent the surface, parametric form of the surface. So, we generally represent the slope by p. So, del z by del x as p, del z by del y the slope of the curve along the y direction as q, and this is the curvature of the curved line, that is del square z by del x square, and it is denoted by r, and curvature along the y direction del square z by del y square is denoted by t, and del square z by del x del y, it is the twist curvature, that is denoted by s. Okay. So, therefore, ds square that we previously obtained as 1 plus del z by del x square, now it can be written as 1 plus p square into dx square plus 2 into p q dx dy plus 1 plus q square dy square. So, expressing this form is known as first quadratic form of the surface. Expression in this form is known as first quadratic form of the surface. So, ds square is written sometimes using certain notations, say E into dx square plus 2f dx dy plus g dy square, where E is 1 plus p square, f is equal to p q, g is equal to 1 plus q square. E, f, g are known as the fundamental magnitude of the surface, and if the parametric curves are orthogonal, then we can see that f will be 0. So, defining a point on the curves, we can find the fundamental magnitude of the surface. Fundamental magnitude of the surface are E, f and g, and E is related to the slope in the x direction, that is 1 plus p square. F is related to the product of these two slopes, that is slope in the x direction multiplied by slope in the y direction, and g is again related to the product of the slope in the y direction, that is 1 plus q square. Okay. So, now we define the slope and curvature as well as twist curvature of the surface at any point. Based on that, we now let us define the principal curvatures. Okay. The principal curvatures will be useful to classify the shell. Okay. Now, let z is equal to f x y be the equation of the surface of the shell or the equation of the shell. Actually, we will not call it this as a plane, because it is a curved structure. So, therefore, it is called as a surface, and this is a curved surface. So, z equal to f x y, if it is expressed in the polynomial form, say it is a generally it is a curved. So, it will be a nonlinear function. So, let us express this in terms of polynomial. Say first I am writing a quadratic polynomial, say x square plus 2 b x y plus c y square. Then if I can also add higher order terms to that. So, z is represented here with the help of polynomial. Okay. Now, let us neglect for simplicity the higher order terms and then proceed to calculate the principal curvatures. Okay. Now, you can see the radius of curvature at any point x y on the surface of the curve, say which is parallel to the x direction, can be found out by this formula that is well known in the differential calculus, 1 plus del z by del x square raised to the power 3 by 2 divided by del square z by del x square. So, this gives the radius of curvature of the curve that is aligned along the x direction. Okay. Similarly, we can find this radius of curvature along the y direction. So, in that case we have to substitute here del z by del y and here del square z by del y. Now, let us neglect for simplicity the higher order terms. The intersection of z x plane. What is z x plane? Z x plane, this is x axis and this is z axis. Okay. So, z x plane, you can see that this plane is z x plane and it intersects the surface. Now, in this z x plane, the y coordinate is 0. So, therefore, this equation of the surface is represented by z is equal to a x square if we consider only this quadratic forms. Okay. Now, for that plane, the slope p of the curve is defined as del z by del x, and it is equal to, if I differentiate this quantity, del z by del x will be 2 a x. Okay. Now, you can see, because this is O is a crown, that is the apex of the shell structure, here the slope is 0 along the x direction. Similarly, along the y direction it is also 0. So, these two curves are orthogonal here. So, therefore, you can see the slope at x direction is 0, that is here we can say at x is equal to 0 at origin. If we substitute here x 0, then the slope is 0. So, slope is 2 a x. So, if I substitute x is equal to 0 in this equation, then del z by del x equal to 0, that means p is 0. Let us now find the curvature. So, curvature is nothing but reciprocal of the radius of curvature. So, if the radius of curvature is denoted by capital R x, then curvature r, that is along the x direction, is defined as 1 by r x, and 1 by r x is nothing but, if we consider the small quantity, that is the slope is small, then this quantity can be neglected, del z by del x, and then we get this r is equal to del square z by del x square. So, del square z by del x square is nothing but 2a. So, we are getting this r. If I now consider the z y plane through the z axis, that z y plane is z and y along the z axis, then in this plane the x is 0. So, therefore, here the equation will be represented by z is equal to a y square, instead of x it will be y square, and therefore, the q, that is the slope along the y direction, will be just 1 by r y, and it will be nothing but this, instead of this, here equation will be z is equal to c y square, c y square will be the equation, and therefore, slope will be 2 c y, and at 0, that at O the slope is 0, and therefore, curvature will be 2 c. So, we get slope and curvature in both the orthogonal direction. Okay. Now, based on that, we now go to find the expression for curvature with respect to a inclined plane. Okay. Let us consider the inclined plane, which is at an inclination of alpha. First, we have considered this plane, say z x plane, and we have found out, and then we consider the z y plane, we have found out the slope and curvature. Now, consider an inclined plane, that is shown by this green color, and the plane is inclined at an angle alpha with the original. This is the plane, this x z plane, that is the original plane x z plane. Now, here the axis is oriented along the other direction. So, this orientation here axis may be x dash axis. Okay. So, in this case, if we denote r t are the curvatures along x y directions, and s as the twisting curvature is del square z by del x del y. Okay. Then along the inclined direction alpha, curvature is 1 by r alpha equal to r plus t divided by 2 plus r minus t by 2 cos 2 alpha minus s sin 2 alpha. This equation comes from the transformation of the derivative along the new direction. So, new direction is the direction alpha. So, therefore, if this direction is denoted by say n direction, we can find, we know the operator del by del n in terms of cosine of the angle and sine of the angle, and with respect to the differential operator with respect to x and y coordinate. Okay. So, when we know this operator, then again when it is used to differentiate this slope del z by del x or del z by del y, or here actually we have to differentiate with respect to new direction. So, if new direction is alpha, that means we have to find the slope along the direction alpha. So, del z by del alpha and del square z by del alpha square. So, therefore, the making this transformation of the derivatives in other directions, we can get this quantity 1 by r alpha equal to r plus t divided by 2 plus r minus t divided by 2 cos 2 alpha minus s sin 2 alpha. Now, if I consider another plane, say beta, what is beta plane? Beta plane is a plane which is perpendicular to the plane that is at an angle of alpha with the original xz plane. Okay. So, in that case, if I just substitute beta with alpha plus pi by 2, that is beta is a new plane, but new plane is orthogonal to this inclined plane. So, this quantity can be directly found out if I substitute alpha with alpha plus pi by 2. Now, you can see when the alpha is substituted with alpha plus pi by 2, then it becomes cos 2 alpha plus pi. So, cos pi plus 2 alpha, cos pi plus 2 alpha is nothing but minus cos 2 alpha. So, this term is appearing with negative sign. Similarly, this sin pi plus 2 alpha, and therefore, this is also appearing with negative sign, and then here it becomes positive. So, we got this r alpha and r beta. R beta is a direction which is perpendicular to the direction of alpha. Okay. Now, twisting curvature similarly can be found out, and it is denoted by 1 by r alpha beta is nothing but r minus t sin 2 alpha minus 2 s cos 2 alpha. So, knowing the value of this curvature along any arbitrary direction alpha and a direction normal to the direction previous direction alpha, that is a new direction beta, we can find the direction of principal curvatures, and here of course, r alpha beta is the twisting curvature. Now, we know that in the direction of the principal curvatures, the twist curvature must be 0. So, based on that, twist curvature on the principal planes vanishes, and therefore, we can write this expression or we can equate this expression to 0. So, r minus t sin 2 alpha minus 2 s cos 2 alpha equal to 0. If I make this equation, then I will get tan 2 alpha equal to 2 s divided by r minus t. So, that is alpha is equal to half tan inverse 2 s divided by r minus t. So, alpha is a direction, that is the desired direction of the principal planes, where there will be no twist curvature. This is analogous to the principal stresses that we have seen in the plane stress problem. So, now substituting alpha in this expression, we can find the principal curvatures. Okay. Substituting alpha here, and after simplification we can find two principal curvatures, 1 by r 1 and 1 by r 2. 1 by r 1 is the major principal curvature, that is r plus t divided by 2 plus root over r minus t divided by 2 whole square plus s square, and 1 by r 2 will be r plus t divided by 2 minus root over r minus t by 2 whole square plus s square. So, two principal curvatures are found, and principal planes, one of the principal plane contains this curvature and another principal plane will be orthogonal to this plane and will contain the another principal curvature, and there will be no twist curvature in the principal planes. It may be mentioned that principal planes containing two principal curvatures are perpendicular to each other, and it is to be noted that twist curvature with respect to this orientation of principal plane will be 0. So, it is clear here, if alpha is the principal direction, then this plane will contain no twist curvature and another principal plane will be orthogonal to this plane, okay, which contain another principal curvature. Okay. Now, let us define a term based on the principal curvature applicable to the shell surface. Okay. If I see that 1 by r 1 is a principal curvature and 1 by r 2 as another principal curvature, and get the product of the two principal curvatures, which is called as Gaussian curvature or simply Gauss curvature. So, if I make a product of 1 by r 1 and 1 by r 2, I will get this r plus t divided by 2 whole square minus r minus t divided by 2 whole square plus s square. So, after simplification you will get r t minus s square. So, Gaussian curvature is nothing but r t minus s square. What is r? R is actually the curvature along the x direction, and T is the curvature along the y direction, and S is the twist curvature. So, knowing this we can find the Gauss curvature. Okay. Now, Gauss curvature is a important parameter which is used to classify the shell in different categories. Okay. So, we shall now discuss the classification of shell based on the curvature, and especially the parameter Gauss curvature is used to classify the shell. Now, broadly the shell is classified as singly curved shell and doubly curved shell. What is singly curved shell? Singly curved shell has a curvature in one direction, in other direction there is the curve has no curvature. So, that means like a, say it is a cylindrical surface, in one direction, in the direction this y direction you will get the curvature, but along the x direction you get this is a straight line. So, therefore, one curvature, because this is the straight line, so radius of curvature is infinity. So, hence the curvature is 0. So, therefore, for such shell, that is which is singly curved shell like a cylindrical shell, the Gaussian curvature is 0, that means R T equal to S square. Now, we have found out this Gaussian curvature, this is R T minus S square. So, if I make this quantity to be 0, then R T equal to S square, that means product of the curvature in the two orthogonal direction is equal to the square of the twist curvature. So, this is example of singly curved shell, Gaussian curvature is 0. Now, let us come to the doubly curved shell. Doubly curved shell, the Gaussian curvature is non-zero. Now, if I see the expression of this Gaussian curvature, this R T minus S square, that is the result of this product 1 by R 1 into 1 by R 2. Now, in one case R T equal to S square, that is the Gaussian curvature is 0, we get classify the shell as singly curved shell. So, example I have shown that it is a cylindrical shell or it may be a conical shell also. So, here if R T minus S square is non-zero quantity, two cases may arise. In one case R T minus S square is greater than 0, in another case R T minus S square is less than 0. So, let us discuss what happens to the type of shell in these two cases. Okay. So, in one case, first let us consider R T R into T is greater than S square. So, in that case we will find that Gaussian curvature is positive, which means that center of curvature lie in the same side of the surface. Say this is the shell surface. So, the shell surface has curvature in both the direction, and therefore, surface is like that this radius of curvature or center of curvature of the radial line lies in the same direction. So, it may be either convex or it may be either concave. Okay. Such type of shell is known as synclastic shell. Okay. So, now let us come to the other type where R T is less than S square. So, what is R T? R T is the product of curvature in two principal directions and S is the twist curvature. So, if this quantity R T less than S square, that means Gaussian curvature is negative in that case. Then we have a shell like that. That means, for curve in one direction, we have the center lying in one side, and for the curve in other direction, the center will be lying on the opposite side. So, this type of surface is known as anticlastic shell. Okay. Now, these two are the main classification of shell, but there are other terms which are also used to group the shell into different categories. but this will also fall under these two categories. These two categories that I told, singly curved and the doubly curved shell are the two main types. Now, let us define some technical terms which will be used to define or group the shell into different types. First, let us define rule surface. A surface is formed by the motion of straight lines over a motion of straight line along a curve. So, this is a curve for example, and this curve is called as directrix, and these straight lines are called generator. So, when the generator moves over the directrix, then a surface is formed, and that surface is known as rule surface. So, straight lines are called generators or ruling. So, straight line has to be moved or straight line has to be ruled along the curve. Okay. So, this is the example of rule surface, that is a cylindrical shell which is also a singly curved shell, falling under the category of singly curved shell. Now, here you see a frustum of a cone, that is also a shell of singly curved group. Why it is a singly curved group? Because the curvature along the one direction is only important, because in the other direction it is a straight line. So, generator is also a straight line which is moved, revolved around the circle to form a cone. So, therefore, it is also a singly curved shell, and single straight line is used to form the rule surface. Therefore, this type of shell is known as singly rule surface. Okay. Rule surface that is formed by the motion of straight lines on its own generating curve. Generating curve is known as directrix. These lines are not necessarily at right angles to the planes containing the n curves. So, there will be one n curves and there will be two n curves are there for the shell, and the generating straight lines may not be at the right angles. In the previous case, we have seen that generating curves are at right angles to the n curves, but in that case the generating curves are not at right angles to the n curves, and such type of shell is known as a conoid. This is also a rule surface, but one end of the generator lies on a straight line and other end rules over a curve. So, conoid is generated by straight line travelling along another straight line at one end. That is, at one end there should be one straight line, and at the other end there will be one curved line. So, that type of shell is known as conoid. Okay. It is also a singly curved shell. The surface is called doubly ruled if at every point two straight lines can be ruled. Examples are hyperboloid of revolution. For example, this type of shell is specially seen in case of cooling tower, and at every point you can see the two straight lines can be ruled. So, one straight line is in this direction and one straight line in this direction. So, this forms a surface which is known as hyperboloid of revolution. So, that is doubly ruled surface. Okay. Now, there are other classes which are known as developable and non-developable surface. Now, definition of developable surface is that any surface which can be developed is called developable surface. The meaning of this is that shells which can be flattened into a plane surface either directly or by making a single cut, straight line cut in the surface. For example, you take a cylindrical shell and you make a cut along the length, and then you apply pressure, the cylinder will be flattened. So, this type of shell has zero Gaussian curvature. So, all developable shells have zero Gaussian curvatures, and all singly curved shells are falling into the category of developable surface, whereas doubly curved shells are non-developable. Doubly curved shells cannot be flattened like that. So, hence doubly curved shell structures are stronger than the singly curved shell. So, cylindrical shell is an example of developable surface. Now, let us see another class of shell is a surface of translation, but this is also falling under the head of doubly curved shell. That is the two main categories, singly curved and doubly curved. Now, ruled surface and surface of translation, there is some difference. Ruled surface is formed by ruling of a straight line, but here surface of translation is generated by the motion of a plane curve parallel to itself over another curve. The plane containing the two curves being at right angles to each other, one of the curve here that special case may also arise, that one of the curves may be straight line as in cylinder. So, surface of translation is also include the ruled surface if one of the curve is a straight line. So, ruled surface is a special category of surface of translation where one curve is a straight line, but here in this example I have shown that two curves are used to form the surface of translation, that is one curve is moved over the another curve, that is this surface is generated by the motion of a plane curve parallel to itself over another curve, the plane containing the two curves being at right angles to each other, and such type of curve you are seeing here, that elliptic paraboloid generated by a convex parabola. So, this is a convex parabola moving over another convex parabola. So, this parabola is moving over another convex parabola, is forming the elliptic paraboloid. So, this is falling under the surface of translation. Okay. Now, there is a very common type of shell which is known as shell of surface of revolution. Surface of revolution is generated by rotating plane curve about an axis lying in the plane of the curve. So, that means if I see here, this is one example of surface of revolution which is a spherical dome. So, this is the plane curve, it is a arc of a circle, and this is rotated about an axis of revolution. Axis of revolution is this, and then the surface form is known as the surface of revolution. So, this is a shell of surface of revolution and it is formed by revolving a part of this circle. The plane curve which is rotating around the this axis of revolution is known as meridian. So, this is a meridional curve, and such type of surface is known as spherical dome, because this will be a part of a sphere. But on the other hand, if a parabola is rotated, suppose this is a parabola, plane curve is parabola and it is rotated about the axis of revolution, then the name of the shell will be paraboloid of revolution. So, that is the difference. Similarly, the ellipsoid of revolution may be also there. If elliptical curve is elliptical meridian is revolved around the axis, vertical axis, then the ellipsoid of revolution is formed. Okay. The curve is called the meridian, that is the plane curve according to which the name of the surface is given. So, for example, when the plane curve is a part of a circle, the name of the shell will be this spherical dome, actually it is called spherical dome, and when the plane curve is a parabola, then the surface is known as paraboloid of revolution. When the plane curve is a ellipse, then surface is known as ellipsoid of revolution. So, this surface of revolution are always doubly curved shells, and it may be synclastic or it may be anticlastic also. Okay. Domes, ellipsoid, paraboloid are examples of synclastic shell, and hyperboloid of revolution that we have seen in case of cooling tower, that example I have shown you. Yeah, this hyperboloid revolution, this is an anticlastic shell. So, the doubly curved shell, that is surface of revolution, may be synclastic or may be anticlastic. Okay. Now, here the pictures that I have shown you are all synclastic shell. Okay. Now, some authors prefer the shell classification based on thickness, but the shell classification based on geometry is mainly, or curvature, shell classification based on curvature is mainly recognized. Based on thickness, the shell is classified into 4 categories: very thin, thin, thick and very thick. Now, how the categories are found? These categories are found based on this thickness to this minimum of the 2 principal curvatures. So, R minimum is the radius, minimum radius, and minimum of the 2 principal radius of curvature is taken to find the ratio. So, if H by R minimum is less than 1 by 200, we call this shell as a very thin shell, and when H by R minimum lies between 1 by 200 to 1 by 25, then we call this as a thin shell, and then H by R minimum when it lies between 1 by 25 to 1 by 10, we call it thick shell, and this ratio H by R minimum when it is lying between 1 by 10 to 1 by 5, we call it very thick shell. The Indian code, that is IS code IS 2210, criteria for design of reinforced concrete shell structures, classifies shell as thin if H by R minimum is less than 1 by 20. So, in our theory of shell, we will mainly discuss the mechanics of the thin shell, that deformation, strains and stresses all will be related to the thin shell. Let us summarize the classification of the shell. Now, in this class, shell is classified based on the curvature. So, geometrical classification I have given, and shell I have defined as a stress skin. Broadly, 2 categories of classification, 2 classes, singly curved and doubly curved. In singly curved shell, the gauge curvature is 0. Doubly curved shell, gauge curvature may be is non-zero, but it may be positive, it may be negative. When it is positive, it is known as synclastic shell, and when it is negative, it is known as anticlastic shell. So, in the singly curved shell, the surfaces that are formed are developable surface and Gaussian curvature is 0. So, that is characteristics. In doubly curved shell, the surface is non-developable and the Gaussian curvature may be positive or may be negative. Okay. Shells of revolution, that is one type, conical shell or spherical dome, all are shells of revolution. Shells of translation, that is formed by moving a straight line over a plane curve, that is straight line is called the generator and the plane curve is known as directrix. That type of shell I have given the example of cylindrical shell. Then ruled surface, that is conical shell is also a ruled surface, and this cylindrical shell is also ruled surface. So, these are some of the examples. In the doubly curved shell, synclastic nature is found in case of spherical dome, paraboloid and ellipsoid. Shells of translation is found in case of elliptic paraboloid, circular paraboloid, and ruled surface is found in case of hyperboloid of revolution. Anticlastic shell, negative Gaussian curvature, and shells of revolution may be there in case of anticlastic nature, and these are hyperboloid of revolution. Shells of translation may be there, that is hyperbolic paraboloids, and ruled surface is another category of anticlastic shell, that is found in hyperboloids of revolution. Okay. So, today I have given the classification of shell based on geometry. I have introduced the geometrical parameters of the shell, mainly the curvatures, and how to find out the principal curvatures based on the curvature in 2 orthogonal direction and twist curvature, and then I use this one important parameter, that is the product of two principal curvature known as the Gaussian curvature, to classify the shell. So, two broad categories of shell are found, one is singly curved and another is doubly curved, and singly curved shells are all developable surface, and in singly curved shell we have seen that shells of revolution, shells of translation and rule surface. Doubly curved shell may be of synclastic nature and anticlastic nature, and we have found in case of synclastic nature shells of revolution, shells of translation, rule surface. Anticlastic nature which is characterized by negative Gaussian curvature, the examples are hyperboloids of revolution, hyperbolic paraboloid, hyperboloids of revolution. So, all doubly curved shells are non developable. So, okay. Thank you very much.